Okay, we've already talked about interference a bit, and we're going to continue on and sort of cover some of those things again, but also talk about resonance and how that occurs in different types of open and closed tubes and on strings and what have you. But first of all waves interfere with one another. All types of waves. Sound waves interfere with one another, light waves interfere with one another, mechanical waves like those killer whales in that Frozen video. Um, and sound waves then will interfere in the same way as light waves in the previous chapter. In fact, in your OP quiz for this chapter, you have several questions that are very similar to things that we dealt with the interference of light. These light waves travel certain distances that are uh, some integer value of their wavelengths. Then do they constructively or destructively interfere? So waves can have either constructive or destructive interference. You should have this down now, but remember constructive interference occurs when the peaks and the peaks line up, and destructive interference occurs when the troughs and the peaks line up like this. If I add these two, I get nothing. If I add these two, I get a wave with twice the amplitude. So waves, including sound waves, can have constructive or destructive interference, and as we saw with the sonic boom, that is a sonic boom. It's constructive interference. For example, we've already talked about this. Let me just go ahead and fill this in. Noise canceling headphones, for example, detect the ambient sound, the noise, and then they produce an out of phase sound wave to destructively interfere or to cancel the outside sounds. And we showed this earlier that if the ambient noise looks like this, then your noise canceling headphones will produce a waveform that looks like this, so that when you add them up, you get, a little bit of noise, but not nearly what you had if you didn't have these noise canceling headphones. So that is an example of noise canceling headphones. Here's a quick test. You should be able to answer this pretty quickly. Now, resonance. Oh, and then also don't forget that we had beats before. We had beats, and remember beats occurs when we mix two frequencies, and the frequency of those beats, the frequency of the beats is equal to the difference in those two frequencies. Okay, and we saw that before with the waveform generator. Now we can have resonance. Resonances occur, let's say that we have uh, a string that's attached to the wall, and you put a wave on this string. I send a wave on this string down to the wall. When it gets here, it's going to bounce off the wall, and it's going to travel back in the other direction. And so when I get something like this, that is a resonance. Sorry, I'm going to have to pause for just a second. I'll come back to this. Okay, so I can have these resonances. Resonance, when I have these waves that add up with one another, and they'll destructively interfere at some points and they'll constructively interfere at other points. Now resonance can occur in a tube closed on one end when the tube is some multiple of 1/4 wavelengths. When the length of the tube is some multiple of 1/4 wavelengths. So what I'm talking about here is the actual length of the tube. At the closed end of the tube, the wave is locked into a node. And that is when the amplitude is 0. So for example, These points are called nodes. When the wave is locked into an amplitude of 0. The air movement there is halted. So here I'm talking about a tube. It's closed on one end and it's open on the other end. And you can imagine that at this end, the motion of the air, it's like it's locked into place. It can't move at that end because it's closed. And so we have a node there. Then at the open end, the reflected wave is at an antinode. That means that I have maximum amplitude. So if this is a node right here, then that means that this is an antinode. And in an open tube, on this end, I have an antinode. That's just the way it is. I have a node at one end, that is the closed end, and then at the opposite end, I have an antinode. When these waves reflect within this resonating tube, they can undergo total constructive interference with other incoming waves, and then that causes a resonance inside the tube. All right, I can draw some pictures here. So if I imagine, these are my tubes. This is going to be our first mode, our first normal mode. This is the when the length of the tube here is equal to 1/4 wavelength. Remember, a wavelength is this. So here I have from here to here. Notice my wave goes only through 1/4 wavelength. This is called the fundamental tone. It's the lowest frequency tone that you can get. So here my wavelength is equal to 4 times L, and so the frequency then is going to be V over 4L, based on our definition of V, F, and lambda. Now, I can also have another tone, so keeping the same length tube, or rather, keeping the same length tube, I will have another frequency. So here, I have to have a node on one end and an antinode on the other end, but I can get a wave that looks like this. See? Node, antinode on this end. In this case, gosh, how many quarter wavelengths do I have? I have 3 1/4 wavelengths. Or the length of this tube is 3/4 wavelength. Here, L, this is called our first overtone. And here, lambda then is 4/3 L. Just setting L equal to 3/4 lambda. Lambda is 4/3 L. And then my frequency is equal to, as we did over there, 3V over 4L. Okay, I can have another tone. This will be the second overtone. And you probably know where I'm headed now. But it's going to look like this. My second overtone is going to have one full wavelength and then another wavelength. So I'm going to have hold on, let me pause for just a second. So I have one full wavelength that goes here, and then I have another quarter wavelength. So it's going to be a total of 5 quarter wavelengths. So my second overtone, as you can guess here, my wavelength then will be 4/5 L. Right, it's just the inverse of this 5 quarters. And then my frequency is going to be 5V over 4L. So we've done enough probably so that you can come up with a generic term for Fn. I'm going to write it over here. Fn, that is the frequency of my various tones, is going to be equal to N times the velocity of the wave, that's velocity of sound in this case, divided by 4L. And N is going to be, our tone, our resonances, is going to be equal to 1, that's for our fundamental tone, 3, 5, 7, and on and on. presumably you can get as many frequencies as you can cram into this one little space. Okay, well, let's go ahead and draw our third overtone though. Our third overtone looks like this. I think that's right. I know I got too many there. Let's erase part of that. Like that. Okay, this is going to be my third overtone. Notice here I have one wavelength and then I have another 3/4 wavelengths. So that's going to be 7/4 wavelengths. And then so my wavelength then will be 4/7 L, and my frequency is 7V over 4L. Okay, so those are our overtones. Look, you can also have this in strings, but in strings, they're going to look different. You know what, actually, I will come back to this and I will create another video because I want you to see also strings. Those are strings that are closed on both ends, and then also tubes that are closed on both ends, are open on both ends, because they're similar but they're different. Okay, so we will come back to that later.